Let's start then. So, yeah. So Nielsen's stochastic mechanics well, is not technically a pilot wave theory like Bohm's theory, in the sense that there is no pilot wave. It's only a derived concept. Still, it's there, and for that reason, the theories have many features in common, which we shall make use of. What the talk is about is an apparent problem with stochastic mechanics, that multi-time correlations in the theory do not correspond to the ones predicted by quantum mechanics. And what we want to do is to point out, using techniques familiar from pilot wave theory, that in fact the problem does not arise. So let me just say a few words about stochastic mechanics. I think many in the audience will know the theory, but I'm the first speaker to talk about it, so I'll just spend a couple of slides on it. And there's a storm outside. I hope you don't hear the. I hope the storm doesn't cover the sound of my voice. Just now. Nielsen's theory is based on a time-symmetric diffusion process. So we've got two stochastic differential equations. One is forward in time, one is backward in time. They are completely on a par. We've got this pair of laws of nature which are completely on a par. We have a mean forward velocity, a mean backward velocity, and we've got suitable Wiener processes for each of these stochastic differential equations. If we take simultaneous solutions at the ensemble level, we get solutions of the corresponding Fokker-Planck equations. Again, one forward in time and one backwards in time. And if we take the sum of these two, this term drops out, and we get a continuity equation for these simultaneous solutions, and the current velocity in the continuity equation is just given by the average of V and V star. And taking the difference of the two equations, we can also see that this expression here, the difference of V and V star, the osmotic velocity, corresponds to this expression here. Now, what Nielsen does is, well, one can write rho as r squared. We can always do that. Assume that the current velocity has this form. That's a non-trivial assumption, but it can be justified. And then the continuity equation takes sort of the familiar form that we know from quantum mechanics, and then the sort of really magic trick defining a sort of mean acceleration in this way. Nielsen, in his original paper, then imposes Newton's law. And from that, he derives this Hamilton-Jacobi-like equation, the Hamilton-Jacobi-Madelung equation. And in fact, these two are the Madelung equations, derived back in 28 or so by Erwin Madelung. And if one assumes that one can put together R and S into a complex function psi in this way, the two Madelung equations are equivalent to Schrödinger's equation. And I've sketched it here for one particle, but the generalization to several particles is completely analogous and straightforward. Now, side remark, this assumption is possibly the trickiest assumption, because it does presuppose that the function S has a very specific multivaluedness behavior, and that assumption seems ad hoc. This was pointed out by Wallström in the 90s, and there's been a long history of trying to justify this assumption. And I'd just like to advertise Maaneli's work on this. He's combined Nelson's theory with the early ideas by De Broglie, and the resulting theory, which he calls Zitterbewegung stochastic mechanics, is one in which the problem doesn't arise in the first place. But this is not the problem we're talking about today. Whoops. There we go. So just to wrap up the introduction, in stochastic mechanics, what we have is the wave function and the Schrödinger equation are derived concepts, sort of emergent features from fundamentally time-symmetric diffusion process. And interestingly, the current velocity of the process is the same as in pilot wave theory, in Bohm's theory. Right. So, given that the current velocities in Nilsson's mechanics and in Bohmian mechanics are the same, it seems intuitive that the two theories should make the same predictions, and indeed, that Nilsson's stochastic mechanics should give the same predictions as quantum mechanics. Is that the case? So Nilsson himself doubted that, and he pointed out the following problem: that multi-time correlations, indeed already two-time correlations in stochastic mechanics, seem to be different from the ones predicted by quantum mechanics. Here's a simple example, and here we're following Blanchard et al. We take a harmonic oscillator in the ground state. This ground state defines a certain drift velocity b for this forward stochastic differential equation, which becomes this equation. It can be solved explicitly, and if one calculates the two-time correlations, expectation value of x of 0, x of t, this is what you get. In particular, it goes to 0 with growing time. This is not what quantum mechanics gives you. One way of calculating the two-time correlations quantum mechanics is noting, well, take the Heisenberg picture, and then you note that for these times, the position operator at time 0 and time t commute. So it's really easy to calculate the two-time correlations. It's just the expectation value of the product, and that's what it is. And in particular, it does not go to 0. It doesn't, in fact, it's, well, it depends on time in this way, but it's oscillating. It does not go to 0. The two calculations give contradictory results. Now, why is that so? Intuitively, what's happening here? I mean, this is a calculation based on the Born rule. So in quantum mechanics, measurement kills interference. We've got, I mean, whether you believe that there's an actual physical process called wave function collapse or not, the formal description is one which corresponds to wave function collapse. Instead, the calculation that Nelson or Blanchard et al. Give in stochastic mechanics uses a drift velocity, which is given by the original uncollapsed ground state. It becomes even clearer that this is why the two calculations give different answers, because as Blanchard and co-workers show explicitly, if in the stochastic mechanics calculation, instead of the drift given by the uncollapsed state, one substitutes drift with S and R here given by the collapsed wave function, then indeed also the stochastic mechanics calculation reproduces the same correlations as quantum mechanics. And now, the big question is, can one justify using collapsed wave functions in stochastic mechanics? Now, after all, the wave function is not a physical object out there in stochastic mechanics. I mean, in textbook quantum mechanics and in collapse theories, one can think of the wave function as something out there which undergoes a certain, perhaps a bit weird, physical process of collapse under certain circumstances, typically when we make measurements. But such a process, a literal process of collapse of this physical wave function, is not something that we can imagine in stochastic mechanics, because there is no wave function that is supposed to undergo these physical processes. However, what we can do in stochastic mechanics is try and model measurements. And the original calculation that Nelson gives is one in which measurement is taken into account just by conditionalizing on the position at the time zero. We learn what the position at time zero is, and we conditionalize on that value. On the other hand, the intuition, sort of a different intuition, is that measurement should be modeled in some more radical way. If we are making a measurement on our system, we are interacting with the system, we are intervening on the system, and so it's reasonable to expect that this intervention might affect the future dynamics. But the question is, how can we model that? Blanchard et al. Themselves suggest that maybe a measurement should be modeled by introducing a new distribution rho, and so a new, so presumably a new wave function with new r and new s, defining a new drift, but that doesn't really work like that. A few years ago, I looked at this specific problem of sort of introducing these probabilistic constraints, and they can indeed be modeled by sort of modifying the wave function, but they require also introducing a nonlinearity in the Schrödinger equation. So the effective effective wave function that one gets and the effective equation that one gets are both different. So just introducing a new distribution is not the right way to model collapse. Modeling collapse should be we introduce a new wave function, but keep the Schrödinger evolution. Lee, would you like to ask your question now? I'm happy to, but you are muted.
You can unmute yourself. Okay, go ahead.
Very quickly, isn't it good to have predictions which disagree from the Schrödinger equation? I found that they were very small, the predictions that arose from this kind of modification of Nelson, and they were interesting. Small but maybe testable.
Well, I guess. Well, in principle, yes. You do want to. It's good to have a theory that's interestingly different from quantum mechanics. But I think the problem here is that if you look at the specific examples, the quantum mechanical prediction is believable and not this this apparent prediction of stochastic mechanics. Certainly, that was what Nelson thought.
We can come back to this.
Yeah. Mm-hmm. Okay. So, right. Here's what we want to do. We suggest we should look at how Pilot wave theory, the Bohm theory, treats measurements. I mean, in a sense, in Bohm's theory, we have an opposite but similar problem. There, the wave function is a real physical object, but it never collapses. So how do we model collapse in Bohm's theory? And we want to point out that that's the natural way of modeling measurements also in stochastic mechanics. And if one does so, then the problem disappears. So I'll really illustrate this by example, and let's start with a very simplistic case first. We just have a particle going through a slit. So this is going to be our position measurement. If the particle goes through the slit, its position must be is narrowed down to the width of the slit. Now, what's happening in this case? We've got two components of the wave. There's one component that goes through the slit, and if we model the screen as an infinite potential barrier, except where the slit is, the rest of the wave is reflected, and these two components don't overlap. So, if the particle goes through the slit, then the motion of the particle is now guided just by the component of the wave that went through the slit, and we can forget about the reflected component. So the wave, insofar as the wave is Pilot wave, it has effectively collapsed. We can forget about the rest of the wave. Only the bit of the wave that has gone through the slit is relevant for calculating the future trajectory of the particle. And now, if we look at the same example in stochastic mechanics, then well, exactly the same happens. I mean, the wave is an effective wave anyway. It's an emergent one, but one part of the wave will go through, the other will be reflected, and if we conditionalize on the position of the particle, if the position of the particle is beyond the screen, then conditionalizing on the position will indeed pick out just the component of the wave function that has gone through. The particle is, or we are only interested, we are only going to be using the component of the wave function where the particle is. So conditionalizing on the particle position is going to pick out that component. And so it's as if the wave function has collapsed. Now, that's very nice, but it's too simple. So what we've done is modeling measurement just using an external potential. And essentially, that's what we had, what De Broglie had in 1927 when he introduced the pilot wave theory at the 1927 Solver conference. He didn't have any more sophisticated way of treating measurements, and in fact, we can't treat measurements in general like that. Here's another simple example. Just take two slits. Now, just like this, we can't tell the difference between sort of conditionalizing on just knowing that, we're assuming that, the particle has gone through, say, the lower slit. Both slits are open. We conditionalize on the particle going through the lower slit. We expect interference behavior. But if both slits are open and we measure which slit the particle goes through, and we know it has gone through the lower slit, we don't want any interference. So we need to do something else in order to be able to model this difference. And the way it's done in Bohm's theory is by including apparatus degrees of freedom. So what we do is we let the particle interact with an apparatus which records whether the particle has gone through the upper or lower slit. So we've got there's the wave function of the particle, the wave function of the apparatus, whatever it is, and the two get entangled. That's a component that goes through the upper slit, the component goes through the lower slit, and then we've got some corresponding wave functions for the apparatus, which correspond to apparatus telling us upper slit or lower slit. Now, note that these two components of the wave, again, do not overlap. And it's not just that they don't overlap because when the particle goes through the two slits, these two components don't overlap. Later on, when the particle moves towards the slit, these two components will overlap. But the total wave function doesn't overlap because these two wave functions of the apparatus are macroscopically different wave functions. You can imagine maybe a pointer pointing up, a pointer pointing down. They are macroscopically different wave functions which will never overlap, only negligibly so. So again, we've got two components of the wave that do not overlap, and therefore, if the particle goes through the upper slit, the future motion of the particle will be guided only by this component. So the future motion of the combined system is guided by this component, which means, but this is a product wave function, so the motion of the particle is just guided by this component. And similarly, if it goes through the lower slit, it's guided only by that wave function. And these are the collapsed wave functions of textbook quantum mechanics. They are effectively collapsed in pilot wave theory. And again, conditionalizing on the position of the particle, whether it goes through the upper slit or through the lower slit, conditionalizing on the position of the particle at the time when it passes the slits, picks out this wave function or that wave function. Now, finally, we may worry about an even more general case, not just about two-time correlations in position, but for instance, at time t0, we might be in fact measuring the momentum, and want to get the right correlations between the momentum of the particle as measured and the position of the particle at the when it's detected later on. So maybe we are measuring the position of the particle using a suspended single slit, like in Bohr's drawing here. And the treatment in pilot wave theory there is actually again quite similar. We have entanglement forming between the particle and the apparatus, and now say we are just measuring the sign of the momentum in the vertical direction, whether it points upwards or points downwards. So we've got this wave function or this wave function coupled with the apparatus wave functions that tell us up or down. And now these two overlap all the time, because the particle is just going through one and the same slit. But these two are macroscopically different wave functions, so they never overlap. So again, these two components do not overlap, and the system, the combined system, is guided either by this or by that. So in particular, the particle is guided either by this wave function or by that wave function. And now, conditionalizing on the position of the particle won't tell us, whether which of these two components the total system is in. But if we conditionalize on the reading of the apparatus at the time 0, then indeed we pick out one component or the other, and in particular we pick out either this wave function for the particle or this wave function for the particle. So if we worry about more general measurements, not just measurements of position, but of other observables, pilot wave theory has a way of modeling measurements and describing what happens in a way that indeed our system, our measured system, does get is guided by the collapsed wave functions of textbook quantum mechanics. And again, everything can be done exactly the same in stochastic mechanics, but now we just need to conditionalize on the apparatus reading, which is how how we actually know we've measured something. Okay, so that's the sort of the crucial result. I mean, that was Bohm's crucial contribution to pilot wave theory in 1952. This treatment of measurements. It allows one to sort of recover the collapse behavior effectively. And if we apply the same way of modeling measurements in stochastic mechanics, we see that the drift velocity after measurement is the one defined by the collapsed wave function of textbook quantum mechanics. So the problem of multi-time correlations has just disappeared. I've got two final slides if I haven't run out of time.
You have, but you can present them. Very nice talk. Go ahead.
Okay. So these are about non-locality, because Nielsen actually made a connection between the problem of multi-time correlations and the issue of non-locality. There's an unpublished talk, but I mean, he did say that on multiple occasions. But the most complete presentation that I know of is in this unpublished talk, and he presents the problem as a dilemma, much like Bell's theorem, between, on the one hand, reproducing the quantum predictions, and on the other hand, maintaining locality. And Nielsen's example is, instead of taking one oscillator, he takes two entangled oscillators, and then he considers the two-time correlations between the position of one oscillator at one time and the position of the other oscillator at the other time, which in fact, I mean, it's essentially the same calculation, which in general is not the same as given by quantum mechanics. And now, the only way of getting the left-hand side to coincide with the right-hand side, if we want stochastic mechanics to give a different result here, we need to assume that the measurement on particle 1 is in fact affecting the drift for particle 2. So the measurement on one particle needs to be affecting the trajectories, the trajectory of the other particle, even if the two particles are at an arbitrary distance from each other. The only chance of solving the problem of multi-time correlations is by embracing non-locality. And that's more or less how Nielsen presented it there, at least implicitly. However, we don't really have a choice in the matter. If we just include the measurement apparatus in the description given by stochastic mechanics, we've seen that the theory indeed automatically yields the same predictions as textbook collapse. So the problem of multi-time correlations goes away, but that means that we do have to accept the non-locality form of the dilemma. And of course, some form of non-locality is to be expected, given the results of the Bell experiments. But this is why didn't Nielsen like this? This is a strong form of non-locality. We do something over here, and the trajectories over there change. So even though he was very much worried about this problem of multi-time correlations, we think that he would not have been entirely happy with its solution. Thank you very much.